This is video 33 in our series Analytical Mechanics. The playlist for these videos is at the website digital-university.org. Now in video number 32 we were talking about a billiard ball struck by a cue stick. The cue stick is perfectly parallel to the surface here and it's right aligned with the center of mass. And in the last video we discussed this in some detail. What happens is that initially the ball skids forward with a linear velocity, and then after a certain time it goes into pure roll. And remember from video 30, the condition for pure roll is such that the linear velocity is equal to the radius of the billiard ball times its angular velocity. That's the condition for pure roll, as we talked about in video number 30. Now, initially, right after the cue ball is struck, it doesn't have any angular velocity. As we saw in the previous video, in general, what happens is the velocity decreases, angular velocity increases because the torque set up by friction. Then there comes a time when this relationship holds and the ball goes into pure roll. And we discussed that in some detail in the last video using kinematics. Now in this video we're going to consider the same type of problem, not by using kinematics, but by thinking of it in terms of angular momentum. And considering angular momentum at different points in the system. So for this video we're really going to be drawing upon what we established in previous videos in 16, 17, and 18 and the different parts of video 19, particularly in 19C, where we demonstrated that for an object its angular momentum has two components. And remember how that worked out now. If we have an object here, it might have a linear velocity and it's rotating also, and we ask ourselves, what is the angular momentum of this object with respect to point O? It has two components. The first component is the angular momentum of the center of mass with respect to point O, and of course that's just going to be the cross product of this position vector with the momentum of the center of mass, the total mass of the object times the velocity of the center of mass. The second component of the angular momentum of this object is the angular momentum of rotation about the center of mass, and that's equal to the moment of inertia about the center of mass times the angular velocity of the object. And of course, we should all be familiar with these equations. The torque is a cross product between a position vector and a force. The torque is also equal to the moment of inertia times angular acceleration, and the torque is also the time derivative of the angular momentum. So let's think of our billiard ball problem in terms of angular momentum, and what happens if we say we take the angular momentum with respect to this point right here, C. Now we can consider, well, first, what happens if we take the torque about point C? Torque is always some position vector, cross product of it with the force. But here, the force is right at point C. It goes right through point C. So this position vector is 0. So the torque at point C is 0. That means then that the time derivative of the angular momentum at point C, that's 0. The time derivative is equal to the torque. That means then that the momentum, or the angular momentum about point C, is a constant, so it is conserved. So, what happens if we consider the angular momentum about point C? Now, let's consider it just before the ball is struck by the cue stick, and let's consider it just afterwards. How before the ball is struck by the cue stick, it's just sitting there, so that's going to be 0. Well, after it's struck by the cue stick, it starts moving, but its angular momentum with respect to point C, that still has to be 0. Because it's constant. It's conserved because this torque is 0. Now, let's think of it in more detail. We know that even though this is 0, it has two components. The first component is the angular momentum of the center of mass with respect to point C. So right after the ball is struck, it does have a velocity, a linear velocity, v0. So its first component, the angular velocity after the ball is struck, is the angular velocity of the center of mass with respect to point C. And what will that be? Well, it has to be a position vector going from C to the center of mass, so that's just this, the radius of the billiard ball, so it's R cross mv0. M is the mass of the billiard ball. But this cross vector is just 0 because the angle between the position vector and our velocity here is 0. So the first component, R cross mv, that's 0. Well, if this equals 0, it has two components. The first component is 0. Let's just keep it like this. This is 0. The second component better be 0. And the second component is the moment of inertia times the angular velocity. Well, the ball is being hit right straight on, so until friction sets up a torque, there is no angular velocity. So immediately after it's struck, indeed, this is 0, and the second component is 0. So when we think of the angular momentum of the ball, before it's struck, it's 0 because it's just sitting there. Afterwards, it's 0. But the two components of this are each 0. So thinking of what is the angular momentum of the system with respect to this point C, that didn't give us any information at all. So let's abandon that approach. And let's consider then, not here, but what about the point here where the billiard ball meets the surface that it's sitting on, this point C. And let's consider it immediately after the ball is struck by the cue stick. So struck by the cue stick, we don't need this anymore because that's going to be any more force, but immediately after it's struck by the cue stick, it is going to have a velocity v0, a translational velocity v0 of its center of mass. Then when it moves across, there's going to be a frictional force. Now, let's ask ourselves this question. what would be the torque at this point C? Well, torque is a position vector across the force. This time it's the frictional force. But here again, this frictional force is right here at point C where it touches the surface. So that position vector is 0. So this is 0. But that tells us once again then that here, the angular momentum at this contact point C is constant. Now, we're considering the angular momentum immediately after it's struck by the cue stick when it has this linear velocity v0. That is our initial angular velocity about our contact point C. Now, at a certain time, in the last video we call it T prime, when it goes into pure rho, then V, we'll call that the final velocity, equals omega r. That's at the time t when the ball goes into pure rho, as you talked about in the previous video. At that time, it will have a certain angular velocity at point C. We'll call that the final angular velocity. So now let's determine exactly what is this and what is this, knowing they have to be equal to each other. Because the angular velocity is constant. Because the angular velocity about this contact point C is constant. Because the torque about that contact point C is 0. Alright, let's consider what is this. Well, it has two components. The first component is the angular momentum of the center of mass with respect to the contact point C. What will that be? Well, we need a position vector going from here to the center of mass. There it is. It's the radius of the billiard ball. So we're talking now about, we're concerned with angular momentum immediately after the ball is struck. It has that velocity v0. What is its first component? It will be r cross m v0. And these are perpendicular. So in terms of magnitude, it's r m v0. Is it positive or negative? Well, let's take this motion to the right as positive, and any type of angular type velocity or consideration that's a clockwise, that's in the same sense as this. So we'll consider that to be positive. Now, so the angular momentum of the center of mass with respect to point C is r cross mv. R is up. V goes to the right. And remember, we have to align the vectors like this when we're taking a cross product. This is mv. So that now when we take the cross product here, the thumb was pointing down and the fingers are wrapping around like this in the positive direction. So the torque is going into the board. The fingers wrap around this. So that's a positive number. So that's the first component of the initial angular momentum immediately after the ball is struck. The second component is the angular momentum of rotation about the center of mass, and that's the moment of inertia times the angular velocity. But this is 0. Right after the ball is struck, the only velocity it has is this translational velocity. So the second component is 0. So that means then that this is just equal to Rm V naught. So let's write it up here. This is Rm V naught. Okay, now let's consider here then the final angular momentum. Final being that time when the linear velocity equals omega r, the condition for pure roll. What would this be? Well, it has two components. The first component is the angular momentum of the center of mass about point C. That's going to be just this, except we're not going to have V naught, we're going to have V final. So this has two components. Component 1 is just Rm V final. And component 2, the angular velocity, or the angular momentum of rotation about the center of mass, that is the moment of inertia with respect to the center of mass times the angular velocity. But at that time, when it goes into pure roll, the angular velocity is the final linear velocity divided by r. So it's this. So this, its two components come out to be equal to Rm Vf plus the moment of inertia for a sphere about the center of mass, that is 2/5 r squared m, and then we have V final divided by r. So this then is the angular momentum at the time when the ball goes into pure roll. And that has to equal the initial angular momentum, because the momentum about the contact point C is constant, because the torque here about point C is 0. So this has to equal Rm Vf plus, and let's make some room, this is the final angular momentum I'm writing down here now. Rm Vf plus 2/5. We have r squared divided by r, so that's just going to be Rm V final. Let's see what we have. This comes about because the initial angular momentum equals the final angular momentum, because the angular momentum about point C is always a constant. It's conserved. So this, and this cancel, and we have V naught equals 5/5 plus 2/5 equals 7/5 times V final, or V final equals 5/7 V initial. So what it tells us is that when the ball goes into pure roll, its final velocity is equal to 5/7, some fraction, that fraction of its initial velocity. And that's consistent, at least, with what we talked about in the previous video. Remember, in the previous video we said velocity is initial velocity minus mu g at time t prime it goes into pure roll. So we know that that final velocity there is going to be less than this because we're subtracting, and sure enough it's just some fraction of it. But when we're thinking now, analyzing the terms of our system in terms of angular momentum, this is the only information that we can derive. We have to use kinematics to determine then what this is and the distance that the ball skids before it goes into pure roll. So when we consider our system from angular momentum, we can derive some information, but it's limited compared to what we were able to derive when we considered our same problem using kinematics.